Usually when we talk about the infrastructure around us, there is this really profound expectation of permanence.
Oh, absolutely. We just expect things to work.
Right. You drive over a major arterial bridge on your commute, or, you turn on the faucet to brush your teeth and you flip a breaker switch,
Yeah.
and you just assume the underlying physical reality of your city is rock solid. It is completely invisible to you. Well, until, of course, the lights go out.
Or a 36-inch water main ruptures in the middle of winter and suddenly your street is a river.
Exactly.
We take the physical world for granted because, by design, modern engineering hides its own decay.
Right.
We only really notice the physical systems keeping us alive when that illusion of permanence completely shatters.
Which is the exact premise of our deep dive today. We are exploring the invisible physical forces that are, quietly and relentlessly destroying government infrastructure.
And massive industrial electrical systems, too.
Yeah.
Right under our noses.
Yeah, but more importantly, we are looking at how artificial intelligence is stepping into this space to track that decay. And we have a really fascinating stack of sources for this.
We do. Some really conflicting perspectives in there, actually.
Definitely. We are pulling from a highly detailed guide by Oxmate on deploying AI-powered predictive maintenance across entire government portfolios.
Right.
And we are contrasting that with the established industry standards on thermal imaging from Heinz Electrical and the Academy of Infrared Training, or ART.
Yeah, those are the folks who train the human inspectors.
Exactly.
Okay.
And to ground all of this in raw molecular physics, we have an incredibly compelling breakdown of arc flash prevention from a group called Restorative Engineering.
And, the tension between those sources is where the real narrative lies here.
Oh, for sure.
You have the established, human-driven, traditional way of keeping civilization running, bumping right up against this completely new, mathematically continuous way of surviving the physical decay of our world.
And the stakes here are just monumental. We aren't just talking about a software update glitching your phone.
No, not at all.
We are talking about preventing massive, lethal industrial detonations. We're talking about avoiding citywide crises that cost taxpayers millions of dollars.
And leave thousands of people without basic human necessities.
Okay, let's unpack this. Because before we can talk about saving a city, we have to look at the microscopic mechanics of failure.
Right. We have to start small.
We really do. We have to talk about a single, tiny, loose bolt inside a steel electrical cabinet.
That is the perfect starting point. Because a multi-million-dollar disaster never spontaneously materializes out of nowhere.
Right.
It begins with microscopic mechanical physics, specifically the interplay between constant physical vibration and electrical resistance.
The restorative engineering source paints this incredibly tense picture of an industrial switchboard.
Yeah, they do.
For those listening, these are the massive steel cabinets managing incredible amounts of electrical power in manufacturing plants or high-voltage facilities.
Right, the big gray box.
Exactly. And the source points out a fundamental environmental reality. These facilities vibrate.
Constantly.
There is this constant low-level mechanical hum from all the heavy machinery, the pumps and motors running around them.
If we connect this to the bigger picture, you have to consider the environment those cabinets actually live in.
Right?
They are bolted to concrete floors in facilities where thousands of horsepower of mechanical energy are being expended every single minute.
Just a massive amount of kinetic energy.
Exactly. And that vibration travels through the floor, up through the steel chassis of the switchgear, and directly into the internal components.
Right.
Inside those cabinets, you have these massive copper bus bars. They're thick sheets of copper that carry the heavy electrical current.
Okay.
And these bus bars are bolted together with heavy hex bolts.
And I guess no matter how tightly a technician torques that bolt on day one, constant mechanical vibration over thousands of hours is eventually going to back it out.
It is an unavoidable mechanical reality. It just happens. And furthermore, you have thermal expansion and contraction to worry about.
Oh, right, because of the heat.
Exactly. When the factory is running at peak capacity, pushing massive current, the copper heats up and physically expands.
Makes sense.
But then when the shift ends and the electrical load drops, the copper cools and contracts.
So it's literally breathing, in a way.
That's a good way to put it, yeah. That constant thermal cycling, combined with the ambient 60 hertz vibration of the facility, slowly loosens the mechanical fasteners.
Wow.
The physical separation between the conductive copper plates begins to grow, even if we are only talking about fractions of a millimeter.
And this introduces the core physical problem here, right?
Yeah.
Electrical resistance.
Yes,
Because
exactly.
the electrical current still desperately wants to cross that joint to keep the factory running.
It has to find a path.
Right, but because the plates are no longer clamped perfectly flush together,
Yeah.
the pathway is restricted.
Yeah, the cross-sectional area is reduced.
So it's much harder for the electrons to flow across that microscopic gap, which causes the electrical resistance at that specific junction to just spike.
Which triggers the phenomenon physicists call Joule heating.
Joule heating.
Right. This is a foundational concept we have to define carefully from the sources. Joule heating dictates that the heat generated by an electrical conductor is strictly proportional to the square of the current multiplied by the electrical resistance.
So it's a mathematical formula.
Yes. The formula is I squared R.
Okay, wait, let me make sure I'm wrapping my head around this. Is it like a kink in a garden hose?
Walk me through that.
So the water flowing through the hose is the electrical current, the I in the formula.
Right.
And the physical kink in the hose, that restriction, is the loose bolt causing the electrical resistance, the R.
Yes, exactly.
So then the physical pressure building up and stretching the rubber right at the kink, that's the heat being generated.
That is an excellent way to visualize it, but pay close attention to the mathematics of that formula, the I squared part.
The square part, yeah.
The heat doesn't rise linearly. Because the current is squared, as that resistance climbs even slightly, the heat generated at that specific localized point shoots up on an exponential curve.
Oh, wow. So to take the hose analogy to its inevitable conclusion, if the water pressure stays constant but that kink gets tighter and tighter, the pressure becomes immense until the rubber violently bursts.
Right. It fails catastrophically.
In an industrial switchgear, that localized heat just keeps escalating over weeks or months. It gets hotter and hotter until it reaches a critical threshold where the air surrounding the copper actually ionizes and becomes conductive.
Yes. At which point, the electrical energy no longer needs the metal pathway.
It just jumps.
It forcefully jumps across the physical gap, traveling directly through the ionized air.
That is an arc flash.
And we need to be very clear about what an arc flash actually is. Because I hear the word flash and I think of like a camera flash.
It is not that.
Right, or it's not a static spark like when you touch a doorknob in winter. It is a catastrophic explosion.
Literally, it is a localized detonation inside a steel box.
It is an explosive release of thermal energy. The temperatures in an arc flash can instantly reach 35,000 degrees Fahrenheit.
35,000? That's insane.
Which is significantly hotter than the surface of the sun.
Wow.
It vaporizes the copper instantly, expanding its volume by a factor of 67,000 in a fraction of a second.
So the metal just becomes a bomb.
Exactly. The resulting pressure wave blows the massive steel doors off their hinges, it melts surrounding infrastructure, and it is frequently lethal to anyone standing nearby.
And the terrifying part about this squared R Joule heating process is that it is completely silent and visually undetectable.
Yes, completely hidden.
Because the heat generated by that failing connection is emitting infrared radiation, which falls entirely outside the human visual spectrum.
We literally can't see it.
Right. A maintenance worker could walk past that specific switchgear cabinet every single day looking right at it and have absolutely no idea that a 300-degree thermal anomaly is building up inside the dark enclosure.
Which highlights the crux of the whole problem here. If resistance strictly equals heat, and the heat is completely invisible to our naked eyes, how does the industry currently attempt to find it?
Which brings us to our sources from Heinz Electrical and the Academy of Infrared Training.
Right, ART.
Yeah, they detail the global standard for managing this exact risk manual thermal imaging.
Right.
So the traditional solution is to basically say, okay, if the heat is emitting as infrared radiation, let's bring in specialized equipment that can translate infrared into the visual spectrum.
Like a thermal camera.
Exactly. Heinz Electrical lays out the standard operating procedure for this. They describe highly trained professionals coming into a facility, opening up the electrical panels and pointing handheld thermal cameras at the switchboards, the fuses, and the cabling.
They're scanning the whole system.
Yeah, they're scanning everything looking for what they term hot zones.
And on the camera screen, a loose connection or an overloaded circuit will show up as a bright, glowing anomaly against the cooler background of the normal, healthy components.
Just lights up.
Right. And Hines correctly points out that identifying these hotspots early is critical for preventing the exact kind of fire hazards and unplanned operational outages we just discussed.
And I want to be clear for anyone listening that this isn't just someone buying a cheap thermal attachment for their smartphone and wandering around a factory.
Oh, definitely not.
The Academy of Infrared Training, or ART, details the immense rigor of this profession. They offer Level 1, Level 2, and Level 3 certifications.
It's a very serious credential.
It is. It's governed by the American Society of Non-Destructive Testing Guidelines. Because the physics involved in accurately reading thermal signatures are just highly complex.
Highly complex and heavily subject to environmental distortion.
What do you mean by distortion?
Well, an ART-certified thermographer has to understand concepts like thermal reflection and emissivity.
No.
For instance, shiny copper actually reflects infrared radiation from other heat sources in the room.
Oh, wow.
Yeah, which can easily create a false positive on the camera. It looks hot, but it's just a reflection.
So the camera lies to you.
Essentially, yeah. And conversely, if a machine happens to be running at a low electrical load on the specific day of the inspection, the loose bolt won't generate enough joule heating to actually show up on the scan.
Creating a false negative.
Exactly, a very dangerous false negative. The thermographer has to actively interpret the physics of the environment to understand what the camera is actually showing them.
That's intense. And Hines also notes that these thermographic inspections are deeply tied to the insurance industry.
Oh, heavily tied.
Because commercial facilities have massive liability policies, and those underwriters know exactly what an arc flash costs.
Millions.
Right. So completing an annual thermographic sweep is often a strict compliance requirement to maintain coverage and keep insurance premiums manageable.
And that specific compliance schedule reveals the fatal operational flaw in how we currently manage physical infrastructure. Did you notice the time frame you just referenced?
The annual sweep.
Exactly.
And just once a year.
The restorative engineering source takes this globally accepted industry standard of the annual thermal scan and absolutely dismantles it.
They really tear into it.
They do. They refer to it as the calendar illusion.
Okay, wait, let me play devil's advocate here.
Huh.
If I'm a facility manager and I'm paying top dollar for an AIR Level 3 certified thermographer to come in with a $20,000 military-grade thermal camera, and they do an exhaustive professional scan of my entire electrical system, how am I falling for an illusion?
It seems like you're doing everything right.
Isn't that the definition of due diligence?
It is due diligence from a legal standpoint, sure, but it is fundamentally disconnected from the physics of failure.
How so?
The calendar illusion is the false belief that physical decay adheres to a human administrative schedule.
Oh, I see.
Thermal cycling, harmonic vibration, and atomic resistance do not pause for 364 days while you wait for your next scheduled compliance inspection.
The physics don't care about your can.
Exactly. The micro movements of that bolt, the creeping increase in electrical resistance, the exponential curve of joule heating it is happening continuously.
So the dynamic nature of the environment defeats the static nature of the inspection.
Yes.
I mean, the human thermographer might walk through the plant in January, open the cabinet, scan the heavy hex bolts, and everything looks pristine.
Right.
The thermal signature is totally normal. They sign the compliance report, the insurance underwriter is satisfied, and the box is checked for the year.
But then reality sets in.
Yeah.
In March, let's say the factory installs a new heavy-duty hydraulic press 30 feet away, which subtly alters the vibration profile of the concrete floor.
Okay.
By May, that specific bolt inside the cabinet has vibrated loose by a single millimeter.
Just 1 millimeter.
Just one. By July, the electrical resistance at that junction has spiked. By September, the I²R joule heating is pushing the localized temperature to critical levels.
And your next human inspection isn't scheduled until the following January.
And by October, the air ionizes, the arc flash detonates, and the facility burns to the ground, fully compliant with its annual inspection schedule.
That is terrifying.
Yeah.
Just totally compliant but completely destroyed.
The source material provides a staggering quantitative metric to back this up, actually.
Oh, what is it?
It states that calendar-based maintenance only achieves a 23% accuracy rate in predicting actual equipment failures.
23%? That's awful.
Because physical decay is a continuous reality, an annual inspection is nothing more than a random snapshot in time.
Right.
You are essentially closing your eyes and rolling the dice for the other 11 months of the year, just hoping the physics don't escalate faster than your calendar allows.
Which means there is a massive, unmanaged execution gap between the microscopic generation of heat and a catastrophic detonation.
A huge gap.
If deploying highly trained humans for annual inspections is fundamentally too slow to catch the physical escalation of joule heating, how do we bridge that gap? We have to move from static snapshots to continuous reality.
Which brings us to the technological intervention, the continuous AI thermal sensor.
Right.
This is where we bridge the gap between digital logic and mechanical risk.
The restorative engineering source explains the mechanics of this beautifully.
They do a great job with it.
Because instead of a human opening a cabinet door and pointing a camera once a year, engineers are taking microthermal sensors and permanently embedding them directly inside these Tier 1 switchgear cabinets.
They live inside the box.
Right. They mount the sensors, wire them into a network, close the heavy steel door, and lock it.
Leaving the sensors in the dark, where they stare unblinkingly at the critical copper joints, the heavy hex bolts, and the load terminals. 24 hours a day, 7 days a week, 365 days a year.
No breaks.
None. They are continuously ingesting the exact same infrared telemetry that the manual thermographer looks at, but they never leave the facility.
And what's crucial here is the sensitivity of the AI software analyzing that continuous telemetry.
Yeah.
Because it's monitoring the cabinet constantly, it establishes a perfect baseline of normal operational behavior.
It learns what normal looks like.
Exactly. It knows exactly how hot that specific joint gets when the factory is running at 100% capacity in the middle of summer, and how cool it gets when the factory is idle in winter.
And because it has that perfect baseline, it isn't waiting for the cabinet to hit 400 degrees to trigger an alarm.
Right. It doesn't wait for disaster.
No, the source explicitly states the software is calibrated to identify a mere 5 degrees Celsius baseline deviation.
Just 5 degrees.
5 degrees. A human wouldn't even register that temperature change against their skin.
No, not at all.
But to the AI, a 5-degree deviation that falls outside the established baseline indicates that the electrical resistance has changed. It catches the I²R joule heating at the absolute bottom of the exponential curve.
It completely bypasses the delay of human analysis. The physical escalation of failure is detected the literal hour it begins.
It's immediate.
But the restorative engineering piece makes a brilliant point here, introducing a concept they call the operational friction point.
What's fascinating here is that this is perhaps the most important concept in the entire discussion of industrial artificial intelligence.
I agree.
They argue forcefully that an alert flashing on a digital dashboard has absolutely zero intrinsic value to the survival of the facility.
Zero value.
Right. Software, no matter how advanced, cannot fix a physical problem.
Right. If the AI detects that critical 5-degree heat anomaly and a little red light starts blinking on a maintenance manager's computer screen in an office 3 buildings away, but nobody actually walks down to the factory floor.
Nothing happens.
The bolt keeps vibrating, the heat keeps escalating, and the arc flash still happens. The operational friction point is the deadly chasm between the digital notification of a problem and the physical execution of a solution.
Which is exactly why the system is intentionally designed to force action.
It forces it.
Yeah. The AI doesn't just send an email. It integrates with the facilities management software to automatically generate and dispatch an immediate, targeted mechanical work order.
Wow.
The system completely bypasses the human analysis phase, isolates the exact cabinet, pinpoints the specific loose bolt, and dispatches a human mechanic with the exact tool needed to fix it.
This completely flips the mainstream cultural narrative about artificial intelligence.
It really does.
I mean, we hear constant anxiety about AI replacing human labor, right?
Yeah.
Rendering mechanics and tradespeople obsolete.
All the time.
But this source looks at the physical world and explicitly says, and I'm quoting directly here, real technology does not replace people. It restores them.
That's a great line.
It is. The AI sensor is permanently trapped in a steel box. It has no hands. It cannot turn a wrench.
It relies entirely on human intervention.
Yes.
The AI performs the continuous, monotonous monitoring that a human being is physically incapable of doing, and the human being performs the physical, mechanical intervention that the software is physically incapable of doing.
Right.
It is a perfect, necessary synthesis.
There's a line from the Restorative Engineering LinkedIn content suite that is just incredibly raw. It says, "Mom still thinks I fix office printers. She misses the point. We prevent industrial detonations."
I love this.
It perfectly frames the gravity of what is actually happening. You have invisible software quietly directing human hands to stop the physical world from tearing itself apart.
But this raises a really important question.
What's that?
If we take this hyper-focused, single-cabinet solution, this philosophy of continuous AI monitoring driving targeted human intervention, and we scale it up.
Oh, scale it up. Okay.
What happens when we apply this exact same mathematical logic not just to a single factory, but to the sprawling, aging physical infrastructure of an entire city?
Which is the perfect entry point to our Oxmain source.
Yes, it is.
It's a comprehensive guide on AI-powered predictive maintenance for government infrastructure. And if you thought the prospect of an industrial arc flash was terrifying, wait until you realize how municipalities are managing the pipes, roads, and bridges keeping you alive.
It's shocking.
Because according to the data in Oxmain, an astounding 78% of government maintenance is currently reactive.
We really need to define exactly what reactive means when applied to civic infrastructure.
Okay, let's do it.
It means governments are operating on a run-to-failure model.
Run to failure.
Yeah. It means the agency tasked with public safety is essentially waiting until a physical asset completely collapses, disrupts public services, or causes a massive disaster, and only then do they dispatch an emergency crew to figure out what went wrong.
It is the calendar illusion scaled up to the size of a metropolis.
Exactly.
They were just watching the garden hose bulge and waiting for it to explode.
Yep.
And the Oxmain source tells a harrowing story that vividly illustrates the fallout of this reactive methodology. Picture this scenario from the text. It is March 2025 in a mid-sized county seat. Buried beneath a major 4-lane arterial road is a 36-inch cast iron water main.
To give you some context, a 36-inch water main is a massive piece of infrastructure.
It's huge.
It is a primary arterial vein for a city's water distribution network, operating under immense pressure.
And this specific iron pipe was installed in 1968. It had been sitting in the damp earth for over 50 years.
Half a century.
Right. It had never undergone a proper structural condition assessment because it's buried under asphalt. I mean, the most attention it ever got was a worker occasionally exercising the exposed valve stems above ground.
Right.
So a severe late winter cold snap hits the region. The sudden drop in temperature causes the frozen ground to shift, placing thermal and mechanical stress on the aging, brittle iron.
Oh, man.
The pipe suffers a massive circumferential fracture and ruptures violently with absolutely no warning.
And the results of a pressurized rupture of that magnitude are instantaneous and catastrophic.
I call it disaster.
The source documents that the break flooded 3 adjacent city blocks with 2.4 million gallons of water before emergency crews could even locate the right valves to isolate the flow.
2.4 million gallons.
Yeah.
And the financial and societal fallout is just staggering.
It's huge.
It required 11 straight days of emergency round-the-clock repair work. The total documented cost was $3.8 million.
Wow.
And that figure wasn't just the cost of welding a new piece of pipe. That $3.8 million included emergency road reconstruction because the water washed away the subbase and collapsed the asphalt.
Oh, of course.
It included environmental remediation for sewer cross-contamination. It included paying out municipal liability claims for flooded local businesses. And most critically, it left 4,200 residents without basic water service in the middle of a freezing winter.
But here is the truly damning detail buried in the post-incident review data.
What's that?
That exact 36-inch pipe segment had been flagged in a manual engineering report back in 2019 as approaching end of useful life.
Wait, really?
Yes. The city administrators knew the pipe was structurally degraded. They knew it posed a significant risk.
So if they knew it was essentially a ticking time bomb in 2019, why on earth did they wait until 2025 for it to explode under a major roadway?
Because of the paralyzing scale of the problem.
The scale?
Yeah. The Public Works Department in that mid-sized county was responsible for managing 1,400 miles of buried water mains.
1,400 miles.
When you are staring at 1,400 miles of aging infrastructure and decades of deferred maintenance backlogs, how do you mathematically determine which specific 10-foot section of cast iron is going to fracture on a Tuesday in March?
Right.
You can't. You can't. Human cognition cannot process that many variables simultaneously. The department was paralyzed by scale, forced to simply wait for the phone to ring with a disaster.
Unless you employ an intelligence specifically designed to process massive multivariable scale.
Exactly.
The Oxmain source offers a devastating counterfactual to the 2025 rupture. They explain that if the city had implemented an AI predictive maintenance model, the outcome would have been radically different.
Completely different.
The AI system would have continuously ingested and analyzed an enormous matrix of overlapping data. It would look at the pipe's cast iron material properties, its 1968 installation date, the specific pH and corrosivity levels of the soil in that exact 3-block radius, the historical data of pressure transients hammering inside the pipe from nearby pump stations, previous break records in adjacent neighborhoods, and the incoming predictive weather patterns of that specific cold snap.
By fusing all of those disparate data points, the AI algorithm would have ranked that exact segment of 36-inch pipe in the top 3% of failure probability.
The top 3%.
And crucially, it would have generated that highly accurate prediction 9 full months before the circumferential fracture ever occurred.
9 months.
9
months. I mean, the Public Works Department could have calmly secured permits, dug up the specific lane of the road on a sunny day in June, replaced the degraded pipe, and paved it back over.
Exactly. No emergency.
No millions of gallons of flooded water, no destroyed businesses, no frozen residents, and just a fraction of the cost. So, if the technology clearly exists to predict these failures 9 months out, why are 78% of government agencies still trapped in that blind run-to-failure cycle?
Because, as the Oxmate source critically points out, having the technology is only half the battle. Having the operational framework to actually deploy it is the real hurdle.
Bureaucracy.
Exactly. Government departments notoriously operate in isolated silos. The water department doesn't share data with the road department. The electrical engineers don't talk to the HVAC technicians.
And historical maintenance records are probably just trapped in filing cabinets or heavily fragmented, messy spreadsheets.
Oh, absolutely. To deploy AI effectively, what is strictly required is a unified, centralized platform, a CMMS or computerized maintenance management system.
The CMMS acts as the central nervous system for the city's physical reality.
Right.
It tracks and contextualizes everything across what Oxman identifies as 6 primary infrastructure domains.
And looking at these domains really illustrates how expansive and totalizing this AI monitoring can be.
Right. The first domain they list is bridges and structural assets.
When monitoring a bridge, the AI is moving far beyond a human inspector just looking for visible surface rust.
Right, because that's too late.
Exactly. It integrates continuous data from physical strain gauges mounted to the steel girders, dynamic traffic load patterns, temperature cycling stresses, and acoustic emission sensors that literally listen for the microscopic sound of metal tearing.
Wow, listening to the metal.
Yeah. The AI predicts fatigue fractures or structural bearing failures months before any distress becomes visible on the concrete surface.
Okay, the second domain is water mains and distribution networks, which we just explored with the 2025 rupture processing, soil chemistry, pipe age, and hydraulic pressure data.
Right.
The third domain covers HVAC and mechanical systems across all government-owned buildings.
This application functions very similarly to our industrial switchgear example.
Okay.
The AI monitors vibration telemetry from massive chiller units, tracks refrigerant pressure differentials, and analyzes the electrical amperage drawn by compressors.
To find the anomalies.
Yes, to predict mechanical bearing failures or motor burnouts weeks before the climate control in a public hospital fails.
The fourth domain is electrical and power distribution. The source specifically highlights the integration of continuous thermal imaging data, partial discharge sensors that detect microscopic insulation breakdowns, and load pattern analytics to predict the exact switchgear arc, flashes, and panel overloads we discussed earlier.
It's all connected.
Fifth on the list is roads, pavements, and stormwater systems.
This domain is particularly fascinating from a data perspective.
How so?
The AI ingests heavy vehicle traffic volumes, correlates it with weather-driven freeze-thaw cycles, and monitors subsurface drainage flow to mathematically predict exactly where the road's base layer will fail and potholes will form.
So they can fix it before the pothole even appears.
Exactly, allowing crews to reinforce the structure before the asphalt physically crumbles.
And the final domain encompasses public buildings and facility systems. This involves tracking elevator motor vibration signatures, monitoring pressure trends and fire suppression sprinkler systems, and even using drone-based thermal scans of municipal roofs to predict moisture breaches and insulation degradation.
It really provides a totalizing, God's-eye view of the city's physical health.
But transitioning from a culture of reactive emergency response to this sophisticated predictive CMMS framework isn't just an exercise in engineering efficiency.
No, it's not.
When you are managing government infrastructure, you're acting as a steward of taxpayer money. And the transition to AI predictive maintenance radically transforms the brutal financial realities of public works.
That brings us to the core financial justification, the ROI, or return on investment, of survival.
Yes.
And the economic metrics Oxmate provides here are simply astounding. Let's start with the baseline capability. AI prediction accuracy across these government pilot programs currently sits at a massive 91%.
91.
Compare that 91% continuous accuracy to the 23% accuracy rate of the human-driven, calendar-based inspections we talked about at the top of the show.
It's just night and day. And that 91% prediction accuracy translates directly into massive operational efficiency.
Right.
The source data demonstrates a 40% reduction in unplanned infrastructure downtime.
40%.
Furthermore, it results in a 25% lower annual maintenance cost overall. Why? Because you are optimizing preventative schedules and paying standard labor rates, instead of bleeding the budget dry on exorbitant emergency overtime pay, expedited equipment shipping, and collateral damage control.
Plus, they note that intervening early fundamentally extends the physical lifespan of the asset by an average of 3 times.
3 times longer.
Yes. If the AI flags a failing $50 bearing inside a massive water pump and you replace it immediately, you save the $50,000 pump from tearing itself apart.
That makes total sense.
The machine lives 3 times longer, delaying the need for massive capital replacement projects.
Let's contextualize those percentages with real municipal dollars. The source provides a financial breakdown for a mid-sized municipality tasked with managing a $2 billion physical infrastructure portfolio.
Okay.
To fully implement this AI predictive system, which includes buying the IoT microsensors, licensing the AI software, and executing the CMS integration, requires an upfront investment of roughly $400,000 to $900,000.
Which, knowing how local politics work, sounds like an incredibly difficult pill to swallow when you go before a city council asking for nearly $1 million for software.
Right. It sounds exorbitant until you present the alternative costs. By proactively preventing those catastrophic emergency repairs, which the Oxmate data notes consistently cost 3 to 9 times more than planned scheduled interventions, that same municipality realizes direct annual savings of between $3 million and $8 million.
So it pays for itself.
The entire technological ecosystem pays for itself in less than a single fiscal year.
I love the story Oxman includes about a specific director of public works because it perfectly illustrates how this technology alters the bureaucratic reality of running a city.
Yes, the director story.
This director was in charge of exactly 1,400 miles of aging water mains, along with hundreds of bridges and public buildings.
Okay.
They were locked in the run-to-failure cycle, burning through $4.2 million every single year, just reacting to emergency pipe breaks and collateral damage.
A completely unsustainable financial drain that prevents any forward-looking civic development.
Exactly. So they changed the paradigm. They implemented the AI predictive models. The AI processed the historical data and mathematically ranked every single pipe segment by its precise probability of failure.
Okay.
In the first year of operation, the Public Works team deployed their crews to proactively dig up and replace 23 specific pipe segments that the AI had flagged as hypercritical.
23 segments.
And here is the truly incredible outcome. Not a single one of those 23 segments failed before the crews reached them. They successfully beat the physics.
Wow. And by neutralizing those 23 specific failures before they ever manifested in the physical world, their emergency repair budget plummeted by 38% in a single year.
38%.
So what does this all mean? The most crucial part of this story is the political victory. When budget season inevitably rolled around, the city council demanded to know how the director was justifying their infrastructure spending.
Right.
In the old reactive paradigm, the director would have simply brought a depressing list of broken things and begged for money to patch them. But this time, they walked into the council chambers and pulled up the AI CMMS dashboard.
They completely reframed the conversation.
They did.
They showed the elected officials the mathematically derived risk scores. They highlighted the specific predicted failures that the crews had preemptively stopped.
Real data.
Yes, they documented the exact taxpayer cost avoidance for every single proactive project. They provided objective, data-driven proof of their responsible stewardship of public funds.
And the result of that presentation? The city council didn't just approve their standard maintenance budget. They increased the department's capital budget by $6 million, for the following year.
That's amazing.
The director summarized the entire experience with a brilliant quote. The AI didn't just predict failures, it funded the program that prevents them.
Wow.
By giving visibility to the invisible physical risks, they secured the exact funding required to ensure the city's survival.
It is a textbook example of how transparent predictive data secures capital in a bureaucratic environment.
It really is.
But this raises a massively important logistical question for anyone listening who manages complex operations, physical assets, or works within local government.
What's the question?
Well, with the physics of failure understood, the safety benefits guaranteed, and the budget justification proven, how on earth does an incredibly slow-moving municipal government actually deploy a massive network of IoT sensors and AI software across thousands of miles of complex infrastructure?
Oh, right.
It sounds like an IT integration nightmare that would take a decade to complete.
When I look at the Oxmain source, I am stunned by how aggressively they approach this. They outline a highly structured 90-day implementation roadmap.
90s.
90 days. It is designed to take a blind, reactive, siloed government department and transform it into a proactive, AI-driven unit in just 3 months.
That's incredibly fast.
Let's really dig into how they execute this because the logistics are fascinating.
It begins with phase 1, the asset inventory and data audit. This is the foundational bedrock of the entire endeavor because you absolutely cannot predict the mechanical failure of an asset if your system doesn't mathematically know it exists.
Makes sense.
This phase requires registering every single piece of infrastructure into the centralized CMMS database. Every water main, every massive HVAC chiller, every bridge, every switchgear. You must import their historical maintenance records, original installation dates, known material compositions, and past failure logs.
And knowing how municipal record-keeping works, I imagine this is a brutal process.
No, it's terrible.
You're talking about unearthing paper schematics from the 1980s, decoding messy Excel spreadsheets, and trying to capture the tribal knowledge of veteran mechanics who know the quirks of a specific pump station but have never written it down.
Exactly.
But you pointed out a really vital technical detail when we were reviewing this earlier. A city doesn't actually need to purchase and install 10,000 physical IoT sensors on day one to start getting value out of the AI, right?
That is a critical misconception the source explicitly addresses. You do not need physical sensors to launch the predictive engine.
Really?
Right. The AI algorithms can generate early, highly useful failure probability models utilizing only that historical baseline data.
Oh, well,
If the AI knows the age of the pipe, the material, the soil chemistry, the historical weather patterns, and past break records in the area, it can mathematically triangulate risk with shocking accuracy.
without a single sensor.
Without a single sensor. The physical IoT sensors are deployed later to sharpen that accuracy with real-time telemetry. But the historical data alone is enough to get the predictive models running immediately.
Okay, so phase 1 establishes the digital map of the city.
Yeah.
Phase 2 is the IoT sensor deployment.
Yes.
This is where you transition from historical data to real-time physical monitoring. You actually send crews out to install the physical hardware, but you don't blindly put sensors on every single pipe and pump.
No, that would take forever.
Right. You strategically install them on the highest risk assets.
Right.
First, the ones that the phase 1 historical data flagged as critical.
Right.
You physically mount the vibration monitors, the acoustic sensors, the microthermal cameras. Then you configure that real-time data feeds into the CMMS and rigorously validate that the physical sensors are actually communicating cleanly with the software interface.
Which serves as the perfect bridge into phase 3 AI model training and pilot operations.
Phase 3.
The AI models begin actively ingesting the real-time sensor telemetry alongside the historical data. They begin training on domain-specific failure inputs, learning the difference between the normal vibration of a healthy pump and the microscopic acoustic shift of a failing bearing.
Okay.
During this phase, they run pilot predictions on a tightly controlled group of 50 priority assets. And this is vital. They do not blindly hand the keys over to the machine.
Right, they check its work.
Yes. They meticulously verify the AI's predictions against physical human engineering assessments to ensure the mathematical model is calibrating correctly to the real world.
It's about building psychological trust.
Absolutely.
The veteran mechanic needs to see the AI flag a pump, take the pump apart with their own hands, and physically see the worn bearing so they know the machine isn't just crying wolf.
Right, they have to trust it.
And once that trust is established, you move to the final step. Phase 4, full portfolio operation.
Dial it up.
You scale the AI predictive models across the entire infrastructure portfolio, and you activate the automated work order generation.
This is where it gets real.
Yeah. If the AI detects that microscopic 5-degree temperature anomaly in an electrical switchgear or a concerning pressure transient in a water main, the CMMS completely bypasses human deliberation and automatically spits out a precise work order to a mechanic's mobile tablet.
And Phase 4 establishes the ultimate operational goal of this entire technological shift, the self-improving loop.
The loop.
It creates a continuous cycle of survival. The constant ingestion of physical sensor data feeds into a daily updated failure probability score for every asset in the city.
Okay.
When a mathematical threshold of risk is crossed, it auto-generates the mechanical work order. The human mechanic physically executes the preventative repair.
Right.
And then, the critical final step, the physical outcome of that repair, was the bolt actually loose, was the cast iron actually thinning, is documented and fed directly back into the AI model.
It learns from it.
Yes. The system continuously learns, calibrates, and refines its own predictive accuracy with every single intervention.
It is a closed loop of continuous physical preservation. When you zoom out and trace the narrative we have walked through today, the scope of it is truly staggering.
It really is.
We started at the absolute microscopic level of physical reality. A single heavy hex bolt vibrating loose by a fraction of a millimeter inside a dark industrial steel cabinet.
Right.
We broke down how that tiny physical separation causes electrical resistance, which triggers the unstoppable exponential mathematical reality of Joule heating and I²R.
And we explored the inherent limitations of relying on the human-driven calendar illusion.
The annual inspections.
Right, the standard practice of sending a skilled thermographer out once a year to look for invisible heat, and how that static snapshot leaves facilities completely blind to the continuous escalation of physical decay.
Resulting in a dismal 23% prediction accuracy rate. And we saw how deploying continuous AI microsensors bridges that deadly execution gap, instantly catching the 5-degree thermal anomaly before it becomes a 35,000-degree arc flash.
Catching it immediately.
Then we took that exact same mathematical logic and scaled it across the sprawling infrastructure of an entire city.
Right.
We detailed how moving away from a 78% reactive run-to-failure culture can predict and prevent a 1968 cast iron water main from exploding under a city street 9 months in advance.
9 months. It's incredible.
We saw how this technology saves municipalities millions of dollars, extends asset life by 3 times, and provides public works directors with the exact dashboard data they need to secure massive capital funding.
Right.
Whether it is the atomic resistance inside a dark electrical cabinet or 1,400 miles of buried degrading pipe, the laws of physics do not care about our administrative compliance schedules.
They absolutely do not. And if I can offer one final takeaway, building on the implications of these sources,
You do.
we spend an enormous amount of time in our culture debating whether artificial intelligence is going to replace humanity or whether we are building systems we cannot control.
Oh, all the time.
But consider the profound legal and societal shift this technology creates for municipalities. Historically, when a water main ruptured and flooded a neighborhood, cities leaned on the legal defense of an act of God or an unforeseeable accident.
Right, they couldn't have known.
But if an AI system is continuously monitoring the physics and it explicitly tells a city council with 91% certainty that a specific pipe will fail in 9 months and they choose not to fund the repair,
Oh,
that failure is no longer an accident. It is a scheduled, known event that was ignored.
that's huge.
The deployment of this continuous intelligence effectively destroys the act of God defense. It shifts the liability entirely back onto human decision makers. It forces us to act.
That is a chilling and brilliant point. It completely redefines municipal accountability.
It really does.
The technology removes our ability to claim ignorance about the physical decay of our world. Like the source said, real technology does not replace people. It restores them.
Exactly.
Thank you for joining us on this deep dive. The next time you turn on a faucet, or drive over a suspension bridge, or walk past a massive electrical panel humming with power, I encourage you to think about the invisible sensors working quietly behind the scenes, tracking the continuous physics of decay.
And the mechanics out there gripping the wrench.
Yes, keeping the illusion of permanence alive for all of us.